Yep. All right, here we go. We're on 2018 now. Let's give it a go. So let's take a look. It says people enter a line for an escalator at a rate modeled by this bananas looking function right here. All right, so apparently from 0 to 300, that's when all the action is. And then after 300, people are not entering the escalator. All right, important to note that they're giving you a rate. This is a rate. It's kind of like a derivative. All right, so now what's this stuff measured in? It says RFT is measured in people per second, right? More evidence that this is given to you as a rate. So RFT is people per second. All right, it says as people get on the escalator, they exit the line at a constant rate of 0.7 person per second. Okay, so they don't give you that visually, but they told you what it was. In other words, what I meant is they didn't give you a name of the function, but I'm going to come up with a name. So if R of t, which I hate that they used R, but whatever, if R of t is the enter rate, then the exit or the leave rate, right, can be, let's make it up, Q of t, and it happens to be constant. So it's 0.7, and again, that's measured in people per second. So there's an incoming rate, and there's an outgoing rate, right? How many times have we talked about this? You're going to have a situation like this. Sometimes it's people coming in, people going out, like in this situation. Sometimes it's sand being pumped onto a beach, sand being pumped out. Sometimes it's water going into a tank, water getting pumped out. It's all the same nonsense. There's an enter rate, there's an exit rate. All right, and then they give you some nice information right here. It says there are 20 people in the line at time 0. So initially, that's our starting amount right here, 20 people in the line. Now, we don't have a name of a function for the amount of people in the line, so you can come up with one. I like to always do capital A for amount. So A of 0 equals 20. So the amount of people in the line at t equals 0 is 20. Now, we don't have a representation for that function yet, but you'll see we'll be able to get one real quick. You don't need to do this right here. I just happen to like to. All right, so let's get after it. So it says how many people enter the line. So how many people enter the line for the escalator during the time interval 0 to 300? Well, you have the enter rate. So if you want to get the net amount of people that entered, right, you should know just integrate the enter rate. So this is a simple question here. So it's basically just going to be the integral of, and I'm not going to rewrite the function. I'm just going to write it as R of t dt from 0 to 300. All right, and that's going to represent the amount of people that enter that line. And if you do this, remember, this was a calculator question in 2018. If you do this in your calculator, you're actually going to get 270, and it should be 270 people. All right, again, why is that? Remember, R of t is people per second. T is seconds. To get the unit for the integral, just multiply your functional unit, right, and your independent variable unit, in this case t unit, and you'll see that the seconds will cancel, so you'll just get people. So that sometimes gives you an idea of what does this integral mean. All right, but you should know that if you want to get a net change in amount, just integrate the rate from one time to the other time. So there's a net change in 270 people. That means that 270 people entered the line. Doesn't mean there's 270 people in the line. It means that 270 people entered the line, all right, during that time interval. So pretty standard stuff. Again, your question couldn't be asked this way because you are going to have to do integrals by hand on your test. So maybe the function that they give you, you will be able to do by hand. Or maybe you approximate this using some sort of, approximation method, whether it's a RAM or a trapezoidal approximation method. So in other words, they give you a table of values. All right, so that's going to be the twist in terms of how they give it to you. All right, so that was a pretty simple, basic question right there. All right, let's go to the next one. It says, all right, during the time interval 0 to 300, there are always people in the line for the escalator. So there's always a line, apparently. It says how many people are in the line at t equals 300. So you want to figure out, all right, how many people are in the line at a certain time value. So again, we had a question like this exactly on your test back in the day. There were 3 things that you needed to consider, right? You needed to consider that initial or that starting amount, right? Then you needed the amount entered. and then the amount, I'll call it exited, right? So those are the three things that you have to consider. All right, so do you know the starting amount? You do know the starting amount, right? The starting amount was 20, so that was 20. Do you know how many people entered? You do, and I'll represent it as an integral though, right? So that would be the integral from 0 to 300 of r of t dt, right? Do you know the amount of people that exited, right? Well, not yet, but you can figure that out, right? If you want to get the amount of people that exited, then integrate the exited rate. So that would be the integral from 0 to 300, right? What did I call it? I already forgot. I called it Q of t, but I could just say 0.7, right? So maybe I'll just do that, 0.7 dt, right? Now you don't add this because these are the people that exited. So you have the initial amount plus the amount that entered minus the amount that left. And this is going to be your answer right here. So now you could even represent this in a cooler fashion and say that, all right, it's going to be 20 plus, right, the integral of a difference is the difference of the integrals. We'll use that in reverse. The difference of integrals is the integral of the difference because the bounds are the same here. So you'd get r of t minus 0.7 dt. Right? And if you think about that, that means that this is the net rate, right? If you have the incoming rate minus the outgoing rate, the difference is the net rate. And when you integrate the net rate, you get the net amount of people. So this would be your answer. So to do this in your calculator, right, you basically just put this in. You'd probably already have this in y1. So maybe you integrate y1 minus 0.7 and then comma x, comma 0, comma 300 if you have an older calculator. If you have a newer calculator, you're basically just putting it in exactly like you see it. You should do it. You should practice it, even though you're not going to have to do this on your test. And at the end of the day, when you do this, you're going to get 80. So there's going to be 80 people at 300. So if I wanted to get fancy with what I was writing before, right, the amount of people at 300 would be 80, right? If I wanted to get fancy. But again, I'd have to somewhere on my paper define what A is, and I haven't really done that yet, right? I could do that, although not 100% necessary for this question, but we'll do it in 2 seconds. All right, but you may have defined A of t before you found A of 300 here. But this is it, all right? So pretty simple stuff. Solid little question. All right, again, could totally ask you this where you're able to actually integrate these by hand or use a table of values or maybe even a graph to do the integral. All right, let's go to part C. All right, so now it says for t greater than 300, what is the first time that there are no people in the line for the escalator? So this is kind of like a weird question in that it's don't overthink it. So you just found how many people were in the line at 300. There was 80 people in the line at 800, right? You know, based off of this, that after 300, right, there are no more people coming into the line, right? They're just leaving at this rate. So if you know there's 80 people, right, total, and they're leaving at the rate of 0.7 people per hour, okay, or per second, you know, how would you figure that out? It's kind of like a distance equals rate times time thing, even though it's not distance, it's not rate, it's not time, right? So basically, there's a couple ways to think about it. You know, maybe you said, all right, I know that 0.7 times some variable, call it t, that represent how many people left after a certain time. And I want to know when that equals 80. In other words, how long does it take for this to happen? All right. You may have just went straight to that your answer is going to be 80 divided by 0.7, which would have been fine too, right? So if you have 80 people and you divide that by people per second, think about this. The people will cancel. You get 1 over seconds. You'll get seconds. This will represent the amount of time it takes to, let's say, process 80 people. I know no one's processing anything, but you can think of it that way, all right? And when you do that, you're going to get this, all right? So that many seconds. Now, that's not the answer, so you got to be careful because that's how long it takes to process 80 people. But remember, we're starting at 300. So the actual time when 80 people are processed, in other words, there are no people in the line, is going to be this. Can you figure it out? Plus that. All right. So your final time here is going to be t equals 414.285 seconds. Okay. All I don't know. So that, I mean, hopefully that made sense. It's almost like non-calculus like question, right? Just kind of like, I don't want to say common sense, but it kind of is, mathematically speaking. That makes no sense. Anyway, all right. So let's go. Let's go to the next part, the final part. All right. So for the final part, it says on this interval, at what time is a number, at what time t is the number of people in the line of minimum? So you knew this was coming, right? They always ask you some sort of minimum maximum question when you have these incoming outgoing rates. It says to the nearest whole number, so we're going to have to round, find the number of people in line at this time. All right. So I'm trying to minimize what? The number of people in the line. So, you know, we're in calc here. So if you want to minimize something, you got to think about, well, what function am I minimizing? I'm minimizing the number of people in the line function. Now, the question is, did they give you that? And they didn't. And we talked about that before, but you should be able to come up with it pretty easy. So in other words, that whole skill of writing an integral function, right? And then it really goes back to, quite honestly, this question right here. Like if you understood how to do this, then you should really understand how to write the function. Because if you think about it, this is A of 300. This is how many people are in the line at 300. So now I don't want how many people in the line at 300. I want how many people in the line at some random time t in that interval. Well, what would change here? You still have to have the initial amount, which is 20, plus the integral now from 0 to, not 300, but 0 to t of that net rate. And that'll get you the amount of people in the line at any particular time t. Okay, so hopefully that is pretty standard to you. So let's do it. So I'll rebuild it, right? So I want the amount of people in the line at any time t. So I know that I have to start with the initial amount that's using that condition. Remember I wrote this? A of 0 equal 20, okay? So that would be 20 plus, and then I can do this as two integrals of 1. I'll do it as 2 first, right? Integral from, well, how many people entered the line up until time t? Well, that's 0. Again, that would come from the fact that they told me that, to that time t. And then of the enter function, which I could say r of t, but for good measure, I'll write r of x dx because this is kind of a dummy variable, right? We don't want to confuse people. This is what makes this a function of t. And then you subtract the integral from 0 to t of 0.7 dt, right? There you go. Oop, I said dt, right? If I was being a good math student, I should be consistent here, right? And this would be dx since I switched my variable to x, okay? And that's it, right? So think about this. Again, this is what you start with. So this is the starting amount. This is the amount entered at time t, right? This is the amount left or processed. Process is a weird word, but I kind of like it. Amount left. Actually, left is bad. Amount that left is what I want to say. Left's a bad word. Amount exited, all right, at time t, all right, because you're integrating the exit rate. So then you're going to get how many left or how many exited. Here you're integrating the enter rate, so you're going to get how many entered. Okay, so this represents this number of people in line function. And again, a lot of times, you know, we don't break it up like that. We say, listen, just write it as a single integral. Your starting amount and then the integral from 0 to t of r of x minus 0.7. And then dx, right? Because this now is the net rate. Integrate the net rate, you get the net rate in people that have entered from 0 to t. So here it is. So you're like, all right, so I want to basically find the minimum of this function on this closed interval. That sounds like a lot like an extreme value type of concept, where the first thing you're going to do, right, if you want to minimize or maximize something, you got to get the derivative. So the derivative is going to be the derivative of this. Well, the derivative sum of the derivatives. Derivative of 20 is 0, right? The derivative of an integral, they undo each other with the variable swap, so it would just be this. And some of you are like, well, I kind of knew that was the derivative anyway, right? Because that's the net rate. And if you did, God bless you. All right, you're good to go. All right, you could kind of jump straight from that. I really would love you to know this concept. And so now what do? I set the derivative equal to 0, right? And so now how do I solve this? I'm going to get r of t minus 0.7 equals 0. So remember, this was a calculated question. So it would be expected that you solve this in your calculator. So what you can do, and I'll kind of do it with Desmos here. Again, this wouldn't be on your test, but as you can put I happen to have R of t here, and I had Q of t there. So I have them separate, right? So I can see where they're equal, or I can say, you know what? Let me graph a third function. This would be like in y3, and it simply is going to be my y1, or in this case, r of x, minus 0.7. Or I could have just put initially this minus 0.7, and I'll shut that graph off, right? So this now right here represents the graph of this, right? R of t minus 0.7, because remember, they gave you R of t. So, all right, I want to find out when it's 0. Well, it's going to be 0 here, and it's going to be 0 there. So those are going to be your two critical values right there. So now this represents a derivative. So now think about this. The derivative is negative here, and then it goes positive here. So there's going to be a relative min here because a prime goes from negative to positive. So the amount of people in the line would be a relative min, possibly absolute min, right? Then we have all of this positive derivative here. And then here, the derivative goes from positive to negative. So that would be a relative max. So technically, I really wouldn't need to consider that value right there. Okay. All right, let me just double check something here because these values look a little wacky. So let's just double check that I put this in correctly. I didn't. That should be a 7. Caught my mistake there. All right. Same concept though, right? Same concept when the derivative goes negative positive. I just noticed that the values were off. Okay. So there you go. So these are the two values you get. All right. So they're critical values at 33.013 and at 166.574. So, all right. So let me come back to my work here. All right. If I'm showing my work, basically my critical values are going to be, scroll down a little bit. I get, call it time subscript 1. The first critical value was 33.013. And then the second critical value, which quite honestly, I don't really need to consider because it was a relative max because of the sign change of the derivative. But I'll throw it down anyway for kicks and giggles. So this is what I get. So now these are your critical points, right? These are your endpoints. So what's the story? How do you find out where there is, in this case, a minimum, right, or an absolute minimum? And that's the whole idea of the extreme value theorem. If you have a continuous function on a closed interval, you're guaranteed to have an absolute max and an absolute min, either at an endpoint or a critical point. So you have to test these values in your function, right, in the function you're trying to minimize, so the amount of people function. So basically, I'm going to test my endpoints and critical points. And if you look at like the answer keys, a lot of times they do this in like a tabular fashion. Test endpoints, test critical points. All right. So in other words, we'll do A of 0. They do it in order sometimes. I'll do it endpoints, critical points, A of 300, A of, I'll call it T1, since I defined T1 right here, and A of T2. Right now, how would I do this? Well, I would plug these values into this function. So A of 0, I already know is 20, right? A of 300, I believe we did before, and we got 80, right? So now to do A of T1, I would have stored this value in my calculator, right? So I got all the decimals, and then when I went to integrate this thing, I would use whatever I stored, the stored value right there. You should do that for fun and practice. Again, I'm not going to go into it because it's not going to be in your test this year. But when you do it, you end up getting 3,803 when you round there. And here you get 158,070, which makes sense that that's a max, right? Or a higher value because it was a relative max. And so now you're looking at this and you want to know when there is, I'm not 3,000, I'm an idiot, 3,000. Yes, 3,000 people waiting in the escalator. I can't read my own handwriting. All right, and this is also a decimal. It's 158. So when you look at this now, this is your absolute minimum on this interval, and you'd state that, right? You'd state something like, "Hey, there's an absolute minimum at T1," and then basically this is all your work here. Okay, this is actually good stuff. If you want to drop an extreme value theorem bomb and say, hey, by the extreme value theorem, you can, but remember, extreme value theorem is an existence theorem. It's just telling you that there's going to be an absolute max and min when you have the necessary conditions. It doesn't necessarily tell you how to find it. You have to be smart enough to take the derivative get the critical points, right? And then test them. Yeah, but that's pretty much it. Just looking at my work here, see if I'm forgetting anything. So standard issue question. So I like it. I love it. It's a great question. Hopefully you crushed it. This is a pretty simple concept. It's just the approach I would take to this problem. Sometimes people take other approaches. This is the approach I take. I will show you one thing because sometimes it appears this way. Let me adjust my window here. All right, so let me go and change my window up here to 5 so this looks cooler. Okay, and instead of graphing the combined net rate, that's the net rate, right? I'll graph the two separate. So the red is the incoming rate and the blue is the outgoing rate, right? So that's another way you could have solved that equation. When those two are equal is when the derivative would be 0. You can see you get the same values that you got there. This is also kind of neat because the exiting rate here, you can actually see it, is higher than the incoming rate. So if you're exiting at a rate higher than the incoming rate, then it would make sense that the line is getting smaller up until this point. And now here, the incoming rate is much higher than the exiting rate, so the line is getting much bigger up until this point, and then vice versa. So that's another way to look at it. You can look at the two incoming and outgoing rates separately, or you can look at the net rate like that, which is the same idea, it just represents the net rate now. When the net rate is negative, the line's getting smaller. When the net rate is positive, the line's getting bigger. Okay? So just another way to look at it. All right, so hopefully you did that. I love the fact that some of you guys are resubmitting your questions to me, so you're doing them. You're getting them wrong with everything you got, right? And then you're looking at the solution video and then resubmitting it. That's how you learn. So I love that. So keep that up. All right, hope all is well. Stay safe.